And now you should see presentation slides, actually.
Yes, I
Uh,
can see the slide now.
Very good. Now we proceed uh, until we can't proceed anymore. So let's go.
All right. So the slides you have, you won't see the videos, but I'll try and explain things to you. I want to present some advances towards high performance printed electronics and circuits. So when I refer to printed electronics, I mean here transistors and circuits. Next slide, please. So if you look at the emerging applications today, on the right-hand side, you saw the applications that you often come across: Internet of Things, mobile healthcare, smart cities, robotics, etc. All these applications, they require flexibility, they require devices to be printed, and they require devices to have performance, which allows a faster computation and communication. Next slide, please. So fast computation, fast communication, flexible, stretchable form factors, large area electronics, distributed sensors, actuators, and computing, etc. So these are the requirements for most of the applications. Next slide, please. But what we see in the printed electronics domain today is many passive devices, some interconnect, some conductive traces, making different patterns, etc. And at best, you see a heterogeneous integration where off-the-shelf the ICs, they are integrated on flexible substrates to compensate or to meet the requirement of the wireless communication and fast computation along with all these passive devices. Next slide, please. So, as we see today, heterogeneous integration. The question comes: is this sufficient as we look forward? The answer is, if it is near term to mid term, yes, it's solving some problems, and we have got many solutions in the market today. If application allows, it's if it's good enough to have rigid ICs on integrated on flexible ultra flexibility, stretchability, and that's where these strategies fail. So you and that's where again, if you are putting lots of transistors in small ICs, that's where again we don't have heat.
Ravinder,
Looking at new
your voice is dropping out.
can you hear me?
Yeah. Is your camera still on?
No, camera is not on.
Okay. Then yeah, we need to proceed.
So yeah. So anyway, these are the areas where we look at high performance computing. And next slide, please. In order to get high performance within electronics domain, if you look at the transit frequency, which is one of the figures of merit when you talk about performance of transistors and circuits, then you will see that it's directly proportional to mobility of material and inversely proportional to the channel length. So as far as material is concerned, within the flexible electronics domain, you have organic materials, metal oxides are being explored, and there are inorganic semiconductors. So organic materials have advantage that you can print them directly. They lead to the electronics, which is inherently flexible. Metal oxides, they provide a slightly better performance, but still not at close, anywhere close to silicon. And then on the right hand side, you have silicon, which is a high mobility material and can provide you high performance as well. But the problem with silicon is it's not flexible. So you have a sort of trade off between flexibility and the mobility that is offered. And then we have the limitations, such as most of the printed electronics tools today, they don't provide high resolution. If you compare with the conventional micro nano fabrication, which is already a single digit nanometer, that sort of scale we are talking about today. In comparison to that, printed electronics, at best, printers are these days able to provide a 1 micron. Numbers in this mathematical equation, you can see how far we are with respect to the performance that silicon based chips provide. Next slide, please. So in my group, we are trying to overcome this problem by exploring various techniques which involve printed